This is a far more common scenario. In a bag, there are 4 green, 3 blue, and 5 red discs. Okay, so how many discs are there in total? 4, 3, 5, that's 12 discs, right? So the silly way of doing this would be to say, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options, right? But because so many of them are the same, and we can account for their different weights with these numbers here, I only really have 3 alternatives, right? Just the 3 represented by the 3 colors. So let's start drawing that out. Is it red, green, blue? Is that what we got? Yes. Good. Red. That was silly. Red. Green. Blue. Okay, so we've got our startup scenario, right? You got to work out the sample space, which we already did, which is 12 in this scenario. So we've got how many red? How many red do we have? 5? 5 out of 12. 4 green. 4 green. So 4 out of 12, which is equal to a third, and 3 out of 12, which is equal to a quarter. So far, so good, right? Okay, now this scenario has 2 different halves, okay, and they would have 2 different diagrams if we needed to draw it, but as you'll see shortly, we don't need to. 2 discs are drawn at random, and the first disc is not replaced before the second disc is drawn, right? So this is an important key phrase. We might put this over the top. Without replacement. Okay. Rather than here, they're explicitly just giving you the numbers from one stage, one game to the next. This is exactly how they change. Well, without replacement, again tells you that the probabilities are dynamic here, right? Whatever happens here, whatever I draw out first is going to affect what happens next, okay? So again, for each case, I've got my 3 alternatives. By the way, if you're like me, and especially when you're doing it in your book, not when you have like enormous meters of space to draw your diagram, if you like me and you sort of do this, you're like, here's my 3, and then you start to draw and you're like, oh no, I've run out of space, and sort of, you know, things go a bit wonky and all cramped together. What you can think about is the fact that you know right from the beginning how many alternatives there will be out here at the end. You know what the total sample space will be. How can you work it out? Why is it, in this case, why is it that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 alternatives at the end? Where does that 9 come from? And the answer is it comes from 3 times 3, right? 3 times 3. If, for instance, on the second go, you know, you've lost one of the alternatives, right? So it was 3 times 2. Maybe you were picking from a different bag, which only has 2 different colors in it, right? Then you're gonna have 3 here, and each one of those 3 branches will have 2. So it'll be 3 times 2, there'll be 6 alternatives, right? If you were rolling a die, and then you were flipping a coin, there'd be 6 times 2, there'd be 12. So you can actually write this side first, and then go backwards, and then you know you won't end up in this situation where everything gets cramped. Anyway, minor thing. Let's have a look at the probabilities now. The first thing I would do is I would say if there's no replacement, then I already know that every single one of these 9 branches, the sample space will be the same. Namely, it's out of 11. There are 11 left. Out of 11, out of 11, 11. Okay, I do this all first so I can get out of the way, and now I can just think about the counting problem. Okay, so I picked the red one. So they started with 5, and now there will be 4 of them left, right? So this will be 4 over 11. How many greens are there left? Still the same number I started with, 4. And how many blues? Same deal, okay? Coming into here, I've picked a green, so the number of reds has not changed, it's still 5. The number of greens has dropped down from 4 to 3, and there are still 3 blues. And then final scenario, original number of reds still there, original number of greens still there, and I'm missing one blue. Okay, now because there are more alternatives here, I might not go through and draw everything. Have a look at the question and see what they're looking for. Part 1, find the probability of drawing 2 red discs. It's easy, it's right there at the top, isn't it? Probability of 2 red discs, okay? By the way, like I said before, just like you don't want to say P equals this, and then P equals this, and then P equals this, because what are all of these? They're all different things, but you don't know what they are. In the same way, if you've gone to the effort to draw a diagram, you might as well use that for your scaffold for where your answers are going to be. Don't just put this off at some random spot. Put it where it belongs, up there, and then everything will be orderly and you won't miss out anything. Okay? So again, using the product rule, we're going to say 5 over 12, 4 times 11. 132, I think. And of course, it's sort of standard form to simplify that. What's the, I mean, I suppose we should have simplified at the beginning, shouldn't we? That's a better way to do it. Happy? Cool. What's the next thing they ask? 1 red and 1 blue. 1 red and 1 blue. Okay, now the good thing about this diagram, is it clearly shows you there are different ways of getting 1 red and 1 blue, because that doesn't tell you anything about order, right? So here's one here, the probability of the red first. And then the other one's all the way down here, probability of getting the blue one first. Okay. So again, we'll go through the branches. 5, 3, and here you've got 3, 5. Okay, now what's interesting is, have a look. Even though we got it different ways, what's happening? Same probability, right? Clearly it's the same probability, because you're always going to be over 12 and then over 11, right? You're going to pick one from the reds and one from the blues, and there's going to be the same number in both scenarios, right? So actually, you can add these up, or you can just double one of them. So now when I double it, 5 over 22. Happy with that? Cool. You can keep going. They start to get trickier, right? But just be mindful. Remember, we learned 3 basic rules that put everything together. You got the product rule, like, okay, you follow along the branches. You got the addition rule, like take 2 different scenarios which cannot happen simultaneously and add them up. What was the third and last one? It's the complement, and it's really powerful and will save you lots of time, okay? If you know to look for it, which means you should always look for it. Example, look at the last one. 2 differently colored discs. 2 differently colored discs. Now, I will write out the sample space just so you can see. Here's red, green, right? Here is green, red, green, green, blue, green, and blue, blue. Now, tell me, how many ways are there, how many different combinations are there that will give me 2 different colored discs? And the answer is there are 6. 1, 2, 3, 4. Hold on, I've missed one. This one. Here we go. Start again. 1, 2, 3, 4, 5, 6. Okay, so using the product rule and the addition rule, of course, I could just add up all 6 of those. But there's a smarter way. Of course, you can use the complement, right? Because the complement of those 6 is these 3. These 3. Red, red, green, green, blue, blue. Okay, which of course, if you went through the whole question, you've already worked out in the previous part, right? So you work out that probability, and then the probability, I would write it like this. Yeah, I've run out of space over there. The probability of different colors, right, is equal to the probability, it's the complement of them being the same, right? This is the way that I would write it. So it's 1 minus the probability of them being the same, and you can work out what that is much faster, okay? Much faster. By the way, don't skip that. Don't skip that. That's a really important logical step. As a marker, I am looking at the fractions. The fractions only tell me so much. You can see that they are often the same, even from different points of view. Okay, but this I can clearly see what's going on in your head, right? So that's really valuable, right? And it'll also save you a lot of time when if you go back and you're checking. You know, it's not just me knowing what was going on in your head. It's you knowing what was going on in your head half an hour ago. You're like, I can't remember. They're just fractions that don't mean anything to me.